Yeah, I checked the store. They say they don't have it in stock, but their other stores might. No, they don't have the stock record for the other stores, but they gave me their addresses. I would have to go to every store and ask if they carry the product. Really? How badly do you need this? Okay, I'll go check the stores and be there as soon as I can. Let's see, how far to the nearest store? 10 minutes, and the farthest is about 3 hours, and then there's all the stores between those. Wait, maybe I should go in a straight path, or just keep checking for the nearest one after I check a store, or how many am I checking? There are 1,151 shops in the state? I need to go to every shop, but I want to get back as soon as possible. Oh! Hey Siri, can you tell me the fastest route to the 1,151 stores in the state?
Let me see. I'm sorry, that is beyond my capabilities.
What? Why?
The possibilities are too numerous for me to accurately compute the optimal route.
In simpler terms, please?
There are too many routes for me to check, and if I tried, it would take a very long time.
Wait, I don't understand. Why would it take long? Don't you do calculations like this all the time?
That is not entirely true. Interfaces that find routes typically use estimations when finding routes with multiple destinations. More importantly, as the number of destinations go up, so does the difficulty of finding the best route. This is due to the problem being an NP-complete variety problem.
NP what?
NP-complete problems are deterministic problems that stem from non-deterministic polynomial problems that…
Wait, this seems really advanced. Start at something easier.
I'll start at something simpler. First, there are problems that are easy to solve, like finding x, addition, multiplication, or basic algebra. These problems are rudimentary to do and easy to check. Additionally, if the numbers get larger, it takes more time to do the operations on them. For example, multiplying 2 times 3 is quick and easy, but doing 230 times 457 takes a bit longer to compute. All these attributes are the characteristics of polynomial or p-type problems.
So p-types are easy to do.
That is correct. Now moving on to more complex problems like factoring. Factoring is a type of problem that gets more difficult to do as you increase the number, but the rate of difficulty moves much faster than p-type problems.
Wait, I thought p-types also get harder as the numbers used get bigger.
Yes, this is true, but for factoring, when the number gets big enough, it becomes exponentially harder to solve. For example, if you want to calculate the prime factors of a 2-digit number like 10, the factors are 2 and 5, but if you calculate the prime factors of a 20 or more digit number, there would be significantly more factors, meaning more time needed to calculate each one.
That still sounds pretty much like p-type.
It is. Factoring the number itself may take long, however checking the answer is relatively easy, since if you have all the prime factors, then you can multiply them all together and see if the product matches. This multiplication to check is part of the p-type problem set.
So factoring can be simplified to just backwards multiplication, which is like a p-type problem?
Factoring and all p-type problems are part of the larger NP-type problem group.
Okay, but what does this have to do with the original question? Wait, what was the original question again?
You asked why finding the fastest routes to multiple destinations takes me and other computers so long to do, and I was explaining that it was due to the type of problem that the question is.
Fine. NP-type are hard to calculate but easy to check?
Yes, now NP-types are also broken down into more segments. More prudently, there are problems that are both hard to do and hard to check, like the one you asked. It is an optimization problem, which is when you are looking for the superlative of the situations, like the highest, the lowest, the fastest, etc. These problems require checking numerous cases and then comparing them to find the optimal answer. These are classified as NP-complete problems.
Computers have to check every single calculation against each other just to find the correct one? Wow, then how is it that math services do this so fast in general cases? Couldn't there be like an endless number of ways to get to 2 points?
Some computers get around all the checks by estimating the closest answer, but that's for cases with limited number of stop points. With the current problem, there are too many destinations and routes that estimating isn't enough.
Is there any way to make the checks faster, or at least make computers faster in their checking, like 2 computers doing it?
Yes. Engineers and scientists have come up with a new method to solve optimization problems in a timely manner.
So what's the method?
Here are some sources I've found for what's the method.
Siri, what's the method for solving optimization problems faster with computers?
Here are some sources I've found for what's the method for solving optimization problems faster with computers.
Can't you just tell me? You were doing so well.
Thank you. A solution the scientists have come up with are quantum bits or qubits.
Qubits?
Qubits are like binary in computers, but with special attributes.
Oh, binary, like those zeros and ones.
Yes, but instead of being either 0 or 1, qubits are 0 and 1.
What? Both?
Yes.
How can you be 0 and 1? Why would that even help?
Here's an example. A computer stores information as bits, so say that going to store A has 4 roots each represented by 4 bits of 0 and 1. Then, going to store B from store A has 6 roots each represented by 4 bits of 0 and 1. The computer stores each root and then checks each A root with all B roots to get the times going from the start to store A and then to store B.
So many.
Now with qubits, each bit will be a collection of 0 and 1, so with 4 qubits, all these possibilities can be stored and checked at the same time, which makes finding the roots faster. This ability to be in 2 different states, like 0 and 1, at once is called superposition.
I guess that's because they're so super in that position.
I didn't quite get that.
Never mind. If this superpositioning qubit is so amazing, why isn't it on my phone, or at least being used by Google Maps?
Qubits can only work inside special computers called quantum computers.
Quantum computers? Oh yeah, quantum bits and quantum computers? Makes sense.
That is correct.
Let's see. Quantum computers use these qubits to do all these calculations faster than current computers. They use these qubits to go through all the roots, and then how would it get back the answer? It can go through all the roots, but if one bit is 0 and 1, how do scientists tell the computer what's the right version of the bit sequence? Do we just look at the bits and decide?
No, the qubits are working as a percentage when dealing with the possible roots. For example, think of normal computer bits being like light switches. A light switch is either up or down, since the light in the room is either on or off. Watch. Even if you get the switch perfectly in the center, the light in the room stays off just like the bit stays 0 or 1. However, look at dimmers. Dimmers work with a percentage of light on and off.
Okay.
Qubits work similarly in making the correct bit sequence have a higher percentage. Like this model, the vector shows a higher percentage towards 0 than 1. This percentage will be compared with the other qubits until the answer contains the sequence with the highest percentage, which will connect to the fastest route.
Excellent! This means we just need a quantum computer, give it all the shelf locations, it will do its fancy superposition with all the possible routes, start comparing them, and give us the best route.
That is not all. Quantum computers can also help in other fields, like finding the optimal configuration of water systems to control water flow in pipes, creating the best route for airplanes to control air traffic, finding the best formula for new medicine to cure diseases,
and helping me get to all 1,151 Dunkin' Donut shops in Massachusetts so my friend can eat an apple cinnamon coffee roll. Now Siri, take me to the nearest quantum computer.
Getting directions to quantum computer.
Oh my gosh! It's in England! Yeah, how badly do you need this again?